safe and healthy. To great pleasure, we have Edgar Shaghoulian today from Cornell University, and he talk for us about replica, wormholes, and black hole information paradox. So Edgar, thanks a lot to give this opportunity to us to hear your talk, and so please take it away.
Sure, great. Thank you guys. It's really a pleasure to give this talk to this group. Some of you who I've met maybe know that I was actually born in Tehran and left when I was a baby, so I don't really remember anything, but I eat a lot of the food and I really want to go back one of these days. So it's really a pleasure to interact with you guys. So thanks for inviting me. Yeah, the talk to us replica wormholes and the black hole information paradox. The Zoom seminar situation is sort of interesting because I've given now similar talks a few times. And so each time I give the talk, there's this pressure to do something different or talk about newer stuff. And it's kind of hard to sustain. But the work in progress here will probably be the slightly newer stuff that I haven't talked about in a seminar on this for those who've already seen it. So let's just jump right in with some overview. And for me, you can interrupt at any point with questions. I don't know what your guys' format is, but feel free to unmute yourselves and ask me anything. So this talk is mostly going to be based on the black hole information paradox, which is succinctly summarized by this graph here. So historically what happened is Stephen Hawking performed what looked like a sort of reliable semi-classical calculation in a black hole background. And he found something puzzling, which is that pure states seem to evolve into mixed states. You consider a situation where you create a black hole through a collapse of some pure state, you let it evaporate, and the radiation looks thermal. So in his computation of the entropy of radiation, he found this curve here that's drawn as the Hawking result. Okay, the entropy just seems to increase and increase, eventually saturates once the black hole stops evaporating, and then stays at some large constant. So what Don Page did several years later is he provided a target of what a correct calculation in a quantum mechanical theory should look like. If a theory of quantum gravity is quantum mechanical, then pure states should not evolve to mixed states. If you start off with an entropy of 0, a fine-grained entropy of 0, it should return back to 0. So what Page plotted was this curve here, which we call the Page curve. The entropy goes up and up like the Hawking answer, but at some point it turns around rather sharply and comes back down to 0. The fact that it starts and ends at 0 is not why we named the curve after him. The two important features here are that in the second half of the curve, it's tracking the entropy of the black hole. So the orange curve is the Bekenstein-Hawking entropy of the black hole. Since it's Hawking radiating and evaporating away, it's getting smaller and smaller. So the area, the entropy is A/4 G_Newton, is getting smaller and smaller, going to 0. And the second half of the Page curve sharply tracks the entropy of the black hole, and there's a sharp turnaround. Those are the two sort of crucial features and why we named it after Don Page, I guess. So this is a target. This is what you would want to compute. This is what you would want to get in an actual quantum mechanical theory. But in the past year, several authors provided an even sharper target of what the correct answer should look like, in particular in a holographic theory. Okay, this was the work using ADS-CFT and various ideas, and they provided some more details behind how the Page curve should arise. Okay, by the way, I'm going to assume you can see my mouse unless told otherwise. Usually that part's been fine, so please let me know if you can't see my mouse. Okay, so what's this talk going to be about? Well, it's going to be about a general mechanism for getting these detailed answers, things like the Page curve here, without assuming holography. Okay, so it's going to be just in semi-classical Euclidean gravity, and we're going to compute for the entropy of radiation in a similar example to the one drawn here and see how we get answers consistent with unitarity. And then we'll try and see what lessons we learned from or about Euclidean gravity and consider some extensions of this general idea. Okay, so that's what this talk is about. Probably everybody already knows that. Let me jump in and consider and talk about the first model that we're going to consider. So we're going to start off with Jakob Teitelbaum gravity. This is a two-dimensional theory of gravity. and it's going to be coupled to a CFT. Ignore the wings part for now. It'll come up in a second. So first consider JT gravity coupled to a CFT. Here's the CFT part of the action. Okay. The JT part is everything else. There's a scalar, a dilaton here, because pure Einstein gravity in 2D is this term, and it's trivial. This is just Euler character, so it's a theory of topological gravity. It's still interesting to consider for testing various ideas, but it's not rich enough for what I would like to talk about. So we consider JT gravity, which adds this this dilaton piece here. Okay, and these is just some boundary Gibbons-Hawking-York terms. So this is what JT gravity looks like. I won't say much about this topological piece. I'll mention it once or twice. But the thing that's going to play the key role is this piece here, the piece with the explicit dilaton. Okay, this is a theory that's been considered a lot in the literature. So I'll make a few comments about it. We're going to supplement the JT gravity theory with what I call these wings. So if you look at this part of the action, the dilaton equation of motion sets r equals -2. In 2 dimensions, the Ricci scalar fixes the Riemann tensor. So the manifold is known, it's just the ADS2. So that's why we have this region here, ADS2, where I have JT gravity plus the CFT. But now we're going to append these flat space regions. So out here, we don't have any gravity, but we still have the CFT. The same CFT that we had is going to live out here. Okay, that's not a crazy thing to do because the gravitational coupling is getting weak near the boundary. In these theories, the dilaton sets the strength of the gravitational coupling. So, normally you have the coefficient of the Ricci scalar is like 1/g Newton, and now it's phi. So phi is like 1/g Newton. So if phi is diverging, g Newton is going to 0. So the gravitational coupling is getting weak. So the gravitational coupling gets weak and weak and weak towards the ADS2 boundary. It hits 0, and then you sort of leave it as shut off out here. So there's really no gravity out here. Okay. So it seems like a reasonable thing to do. We'll try and improve on this later when I talk about applications of these ideas to just directly in flat space. But for now, this is the model. We'll consider, various authors considered this for various reasons. It was, putting these flat space wings on ADS was first considered by Roca in the context of the information paradox, I think around 10 years ago now, or 12, over 10 years ago. These authors, Arnos, Hoffman, and Krutov, considered doing this in the context of defining something like an S matrix in ADS2. And then the rest of these authors were part of the authors who last year, provided the sharper target of what a correct calculation in a holographic theory would look like. So, this setup has a rich history. And in fact, if you think about where ADS-CFT came from, it was, it's a decoupling limit of a, stack of D branes in asymptotically flat space-time. So you zoom into the branes and ignore the flat space region. So this you could think of as putting back in the flat space region in a sort of toy model kind of way where you could actually compute things. Okay, so that is, that's the setup. These are called wings because they look like airplane wings. And that's the model we're going to consider. So in particular, we're going to have the Hawking radiation come all the way out to this region, and we're going to measure the entropy of Hawking radiation out here because it's easier to do. There's no gravity. You don't have to worry about different variance or anything like that. You can just pick a region, define a region, and compute the entropy of that region, and it's just going to make our lives a lot easier. Okay, that's why we construct it this way. I'll make a pretty tangential comment. In the literature, often the first thing that's done in this JT gravity theory is that a contour is chosen for the dilaton along the entire imaginary axis. So a contour for the path integral. And if you choose that contour and you integrate out the dilaton, it acts as a constraint. Okay, it's basically like a Fourier piece that imposes the constraint r equals -2. So r equals -2 came from the equation of motion for phi. But if you choose this contour for the dilaton along the imaginary axis, it imposes it exactly, quantum mechanically, as a constraint. I don't want to do that. What I'm going to be talking about in this talk is purely saddle point analysis. So I don't need to worry about, well, I don't yet need to worry about contours of path integrals and things like that. I'm just going to look at saddles of the theory and see which saddles dominate. I'm making this point because, the dilaton, where JT gravity comes from is you can think of it as a dimensional reduction of 3D pure gravity or a dimensional reduction of higher dimensional gravity in like the near horizon region of near extremal black holes. And in those contexts, phi serves as the size of the transverse sphere. And in any example where we really understand the rules of quantum gravity, we integrate over positive semi-definite metrics. Okay, we don't integrate over complex or negative metrics. So in particular, phi, you would want to be positive, okay? So when you integrate over the entire imaginary axis, which you can think of as rotating the entire real axis, you're sort of integrating over negative or complex metrics, and I don't really want to do that because it's not super clear that that is really a good model for a theory of gravity. So just making the point that here, we're not going to rely on that. We're just going to use saddle point equations, and that will be enough. Okay. All right. So I said I won't say much about this topological term. One of the main things it'll do is it'll suppress higher genus saddles. If I imagine doing the path integral now over metrics and different topologies, this thing is the Euler character. So as I add handles, as I increase the genus of my surface, this is going to lead to a suppression of such a saddle in the path integral. So for that reason, I won't consider arbitrarily complicated, higher genus saddles. Okay. All right, that's the model I'm going to consider. Any questions about it before I move on? Okay. So what do we like? That is the model we're going to talk about, but what's the state we're going to consider? Well, for the information paradox, a useful state to think about is the thermal field double state. And now it's going to be a slightly modified thermal field double. Often we talk about this in the context of ADS CFT. Now we're talking about it in the context of ADS coupled to these flat space regions. So we want to set up the thermal field double. Well, we know how to do that in flat space. We want to set up the finite temperature state. That's just the thermal cylinder, okay? So here all I'm saying is that you just compactify Euclidean time, and that's the finite temperature Euclidean manifold for Minkowski space. But now we need the ADS part. So the way we do that is we just chop it at a certain point and glue on Euclidean ADS2. Okay, that's just the hyperbolic space. So this is the Poincare disk. So we glue that on. By the way, the coloring, if it's not clear, the blue regions are always going to be regions where I have JT gravity or some theory of gravity. In this talk, will basically always be JT. And the white regions are where there is no gravity. Okay, so that is the ADS2 region where we had JT gravity. This is the flat space region where we just have the CFT. So this is the relevant Euclidean manifold. And to prepare the thermal field double state, we path integrate over the bottom half of the cylinder to prepare a state at t equals 0, which we can continue to Lorentzian time and then evolve forward and backward in Lorentzian time. Okay, so that's how we prepare the thermal field double state. And here I've just blown out the cylinder into the plane. Okay, so this picture here is like looking down the cylinder. It's just the cylinder's plane map. It looks like this. Okay, and t equals 0 gets mapped to this region here. So this side is one side of the thermal field double, and the left side is the other side of the thermal field double. Okay, and as usual in the Euclidean manifold, the interior of the horizon is not visible. The bifurcation point is like the center of this picture. Okay. Okay, that's the state we're going to consider. So I said we prepare it at t equals 0, and then we can evolve up forward and backward in time. And now I can pretty quickly state what the problem is. So it's not going to be exactly the problem I introduced about an evaporating black hole. That is just a little more annoying to deal with because that is really just a strongly time-dependent situation. And whenever you have time-dependent backgrounds, the Euclidean methods don't really work. I mean, you'd have to complexify everything and look for complex saddles or something like that. So I want to use Euclidean methods, so I'm not going to consider really the evaporating black hole. Here, if we evolve upward from t equals 0, what I've drawn here is basically the entanglement in the thermal field double state. Okay, you can compute what the entanglement entropy is analytically, and we'll talk about that in a second. But you can also just draw this picture, which makes it easier to understand what is going on. So here are the horizons. There's one horizon, there's the other horizon. And the way the entanglement across the thermal field double looks is that there are these entangled pairs on either side of the horizon. So the blue mode is entangled with the blue mode, and the green mode is entangled with the green mode, okay? You have both things like Hawking radiation and these sort of infalling modes. because this is like the Hartle-Hawking state. Okay, the black hole lives eternally. Now, let's say we wanted to compute the entropy of radiation on this left region union this right region. Okay. Well, we see at t equals 0, for example, that the green mode is captured by the region. So there's no entanglement due to the green modes. And the blue modes are both missed by the region. So there's no entanglement due to the blue modes. Okay, imagine each of these pairs contributes something like log 2 worth of entanglement entropy. But if I evolve upwards in time on both sides, then something funny happens, which is the green mode, which was captured on the left, continues to be captured on the left. But on the right, it's no longer captured by this region here. So we have some entanglement entropy that's due to the entanglement of this green mode with its partner, which is not captured by our surface. Okay, so its partner Bell pair is missing. And similarly with the blue regions, at t equals 0, they were both missed by the t equals 0 surface, but as evolved until later time, the right region now captures one of the blue modes, but the left region does not capture its partner mode. So you also get an increase in entanglement from those guys. This basic picture shows you why the entanglement entropy computed a la Hawking seems to increase indefinitely in time. If you evolve both sides in time forward, then you just increase the entanglement indefinitely, and you get something like this, what's drawn here, this dotted line is the Hawking answer for the entanglement entropy. And in this case, it really does increase linearly in time forever because this black hole, this thermal field double state, never evaporates away. All right. The analog of the page curve, which just means the answer that's consistent with unitarity, is the one that's drawn in red here. Basically, the entanglement entropy should not exceed 2 times the black hole entropy. Okay, this is using the idea that a black hole can be thought of as a quantum system with A/4's worth of degrees of freedom, and you can't have entanglement entropy that exceeds that amount. You can entangle yourself with a quantum system with A/4 degrees of freedom and have an entanglement entropy greater than A/4. So it has to saturate at that value. There's a factor of 2 here just because there are 2 black holes. There's the one on the right and the one on the left. Okay. So this is what the unitary answer looks like, and it's the one that we would want to compute. And it's the one that I will talk about how to compute. One final thing to say is that people might be familiar with the fact that the thermal field double state has some time translation isometry. That goes, that Killing vector goes up on the right and down on the left. So if I had put this region that I'd drawn in the left region at some positive t instead at some negative t, then nothing would happen in time. The entropy would remain constant because that's just an isometry where you evolve upward in time on the right and downward in time on the left. Nothing should happen, and that's indeed true. That's why I'm evolving upward in time on both sides, because that is not an isometry, and you'll get some non-trivial behavior of the entanglement entropy when you do that. The final comment is this was a cartoon, but we actually know how to compute analytically what the entanglement entropy is. You know, this global state is pure. So instead of considering the entropy on this left region union this right region, I can compute the entropy on the complement, which is just the region that cuts across here. That is the entanglement entropy of a single interval in 2-dimensional CFT. We know what the answer for that is. So you could compute it, and that's how you get, for example, the details of this curve, the fact that it increases linearly. That wasn't obvious from the pictures and words that I said. But if you compute, you'll see that at late times, after a few thermal times, the entanglement entropy increases linearly, and at early times, there's some funny behavior like this. So that you can compute analytically. These pictures are just useful for intuition, especially in higher dimensions where we don't have exact formulas. These pictures still help form some intuition. All right, so now we've covered the theory and the state. Any questions? I think we're going to accelerate from here on out. So, okay, we want to compute the entanglement entropy in field in this setup. So I should review very quickly how entanglement entropy is computed in field theory. So when there's no gravity involved whatsoever, we want to compute the von Neumann entropy or the fine-grained entropy or the quantum entropy. It has various names, but it's this quantity, trace rho log rho. So R here is gonna, well, stands for region generally, but in this case, it's gonna be the entropy of radiation. That's the thing I'm gonna be concerned with computing. So we wanna take the full density matrix of our system, trace out the region that doesn't correspond to the radiation to construct a reduced density matrix, and compute minus trace rho log rho, okay? That's the von Neumann entropy. That's the thing that Hawking purportedly computed. And the way this is often done, because there's this logarithm of this operator, which is a kind of a pain, you do it through the replica trick. You construct this quantity trace rho to the n. Okay, you construct what are called the Renyi entropies, which are this combination of trace rho to the n. And then you recover this quantity by analytic continuation of n goes to 1 and doing this combination. Okay, what is this trace rho to the n object? Well, it's a partition function on a topologically non-trivial manifold. So people talk about this various ways. You can think about it as a correlator of twist operators. I won't use that picture here. You can just think of it as a partition function on a non-trivial manifold. So for n equals 2, it looks like this. If I want to compute the entropy of the left region union the right region, I make 2 copies, or more generally n copies, and I sew them together across the cuts, across the region whose entropy I want to compute. And so then I have some topologically non-trivial manifold. Okay. These points on this, on this manifold are singular here. Okay, corresponds to some conical excess. Okay, these equations tell me that this partition function is related to the Renyi entropy in this way. So in particular, if I have a large entropy, which we'll see in a second is what happens in the context of gravity, this implies an exponentially small Zn, okay, just because Zn is related exponentially to the entropy, in this case, the Renyi entropy at some finite n. All right, so this is how you compute entanglement entropy, or more generally, Renyi entropies in field theory. So let's go to how we do it in gravity. It's very similar. We do the same thing. We want to compute the entropy of this region union this region. Again, I'm drawing it for the case n equals 2. But now the difference is there's no blue here because I haven't introduced gravity yet. In a theory with gravity, you're not allowed to pick the manifold, right? That's the whole point. Gravity is a theory of the manifold. You, in general, path integrate over all geometries, and maybe there's a saddle point that corresponds to a nice classical geometry or what have you. But generally, when you have a nice time-like boundary, as we do in the ADS case, you just set boundary conditions, and then you path integrate over all internal geometries consistent with those boundary conditions. Okay, so you set boundary conditions, and then you let gravity fill in the geometry how it chooses to. So one obvious way to do it is to fill it in with 2 independent hyperbolic disks. Okay, but now phrasing the problem this way, it becomes clear that there's another way to fill it in, which is to draw a wormhole that connects the 2 sheets, okay? Now, in the context of JT gravity in ADS2 plus CFD, you can show that this is actually a saddle point, but in general, it doesn't really have to be a saddle point. The point is there exists some, maybe it's off shell, but there exists some configuration like this one, and it should be included in your path integral, okay? Or one choice is to include it in your path integral. And at general n, you can draw, these sort of fully connected wormhole type saddles. And at n greater than 2, you see that there are lots of things you can do. You can draw this fully connected saddle. You can draw the fully disconnected one, which fills in independent Euclidean hyperbolic disks on all the sheets. You can draw partially connected ones. So there's just some explosion of different saddles you can draw. But the relevant ones for us are going to be this one where you filled in independently, and this one where you're connected by a wormhole. Okay, this saddle is like the Hawking saddle. Okay, if you translated Hawking's calculation of the entropy of radiation into a calculation where you use the replica trick to recover, I mean, he didn't use the replica trick, but to recover his answer, you would pick this saddle and you would totally ignore this saddle. And we'll see that to recover Page's answer for what the unitary curve looks like, you would want to pick this saddle. Okay. Well, in particular, Page's curve has some transition. So that transition where the curve either turns around and goes down in the case of an evaporating black hole, or in our case, it increased and then saturated at 2 times the black hole entropy. You start off with this saddle as the dominant saddle, and then there's an exchange of saddles, which nowadays a lot of us confusingly call the Hawking-Page transition, where you go over to this saddle, and that has an entropy that's constant in time. All right, this is at finite n. Okay, this is at n equals 2, for example, but the question was to compute for the entanglement entropy at n equals 1. That to me is mostly historical. I mean, if you computed the Renyi entropies, you could construct similar paradoxes and argue them away by these saddles. But for historical reasons, we'd like to understand the entanglement entropy, which is an n goes to 1 limit. And basically what happens is that these replica wormhole saddles, they leave an imprint as n goes to 1. It's a little confusing when you first think about it because there's no wormhole at n equals 1. This is something that you can draw a nice picture of at finite n, but at fractional n, or as n goes to 1, it seems like they would want to disappear. But of course, there's some analytic continuation from finite n to n equals 1 that you're doing. And these effects at finite n can leave an imprint, as they do whenever you do a replica trick. And what you see as you work through it, and I'll give a quick kind of derivation of this, I think in the next slide, is that they reproduce what's called the island rule, which is this equation written here. Let's break down this equation. This equation says if you want to compute the entropy of radiation in some region R in a theory of gravity, and let's say the region R is in a theory where there's no gravity, just for simplicity, here that's exactly what we're doing. These white regions don't have gravity. What you need to do is consider the inclusion of additional regions, which are called islands, in the gravitational part of the spacetime. Okay, you can have many, here I've drawn one island, but in general you can have many sort of disconnected islands. That's why I put this kind of tongue-in-cheek footnote about the archipelago rule. The archipelago is a chain of islands. So you can have a lot of various islands in the rule. In general, those aren't going to be the answers that dominate, but you want to consider the inclusion of all possible islands, I. You want to compute this quantity, which is the gravitational entropy of region I. Okay, the gravitational entropy of some codimension 1 region in general is like A over 4G in Einstein-Hilbert gravity. In these dilaton gravity theories, it's just the value of the dilaton at the endpoints. Okay, that's, like I said, the dilaton captures the dimension of the transverse sphere in dimensional reductions. So it's natural that the gravitational entropy is phi over 4G instead of just area over 4G. Phi plays the role of area. So you can be the gravitational entropy, which is phi over 4G at the 2 endpoints. You add it to what I've called the effective entropy. This is just the matter entropy on the region R union I. Okay, you add those two things. This constructs what's called the generalized entropy. And you want to extremize this quantity over all possible inclusions of islands. So you want to find an extremum of the generalized entropy. And then if there are many of them, you want to minimize. You want to take the one with the smallest value of the generalized entropy. Okay, that is a bit of a mouthful, but that's the procedure that was hypothesized in the last year by several different papers when they thought about these problems in the context of ADS-CFT. They used things like the Ryu-Takenagi rule and deduced that something like this is true for holographic theories. So maybe something like this is true also for non-holographic theories, just theories of gravity. So they called it the island rule, basically because there can be these disconnected regions, right? This looks, this looked crazy to me when I first saw it, because you just go and introduce regions and there's an entropy on the left-hand side and an entropy on the right-hand side. So it's a little bit confusing. The way to think about it is that the entropy on the left-hand side is a fine-grained entropy. Okay, it's really computing something like the von Neumann entropy, trace rho log rho. Okay, whereas this S, I've written S effective because it's more like a coarse-grained entropy. It's an entropy on a fixed gravitational spacetime. Okay, so it's like what Hawking would have computed. So they're slightly different quantities. They're not the same sort of matter entropy. They both are some sort of matter entropy, but the expression, the thing on the left is a fine-grained entropy. It's the thing you want to compute. Okay, so the replica wormholes actually imply this rule as you continue n to 1. And this rule gives you exactly this page curve, right? The way that that happens is if you apply this rule in this setup that we've been talking about, you'll find that there's some island region that extends from a little bit outside the left horizon to a little bit outside the right horizon. Okay, that's can actually find such an extremum. And now we can draw our pictures again. This is why these pictures are fun and useful, of these modes that are being captured or not captured. And whereas before, at some later time, the blue mode was only one of the blue modes was being captured, and only one of the green modes was being captured, leading to an increase in entanglement. Now, the island allows you to capture the missing blue and green modes. So now the region R union I has both blue modes and both green modes, so they don't lead to an increase in entanglement. Okay, so at early times t equals 0, both green modes, there's no island at early times at t equals 0. Both green modes are captured by region R, and both blue modes are missed by region R, so they don't lead to any amount of entanglement. And at late times, because of the island, both green modes and both blue modes are again captured. So that's how you see that the entropy kind of saturates and stays constant in time and gives you the page part of the curve. Okay, the fact that there's no island at early times is how you recover the Hawking answer, because Hawking never used islands or anything, or replica wormholes or anything like that. The way you recover that part of the answer is that there are no islands at earlier times. Okay. Any questions about either the island rule or the replica wormhole?
May I?
Okay. Yeah, please.
How justified is using the replica trick in this problem? Because maybe the effect of creating the island is just a fictitious effect of replica trick and analytical continuation. And in reality, such thing does not exist. So how sure people are about these islands and replica trick?
That's a fantastic question. Let me maybe try and rephrase your question, but correct me if the rephrasing is not what you're getting at. You might say that the replica trick, well, it's literally in the name, it's just a trick to compute the entanglement entropy, and you didn't have to do that. You could have directly computed trace rho log rho without ever introducing replicas. Is that roughly your question, Hassan?
Yes, yeah.
Yeah, so that's a great question. It would be wonderful to understand directly what, what like replica wormholes are when you don't make replicas. And I like to, usually I like to give an analogy, which is in the context of spin glasses, which are disordered systems that have a lot of rich physics. They're supposed to be models for glasses like in the real world, like on window panes. There's a beautiful solution of a certain spin glass model by Giorgio Parisi, which used something called replica symmetry breaking. He wanted to compute the entropy of the system. He used the replica trick. And originally people did this in the 70s, or I forget when exactly, 60s maybe. Sherrington and Kirkpatrick did this for their model of the spin glass. And they found answers that didn't make sense. And entropy became negative at low temperatures, and they got all these nonsensical answers. And what Parisi discovered is he did the calculation, and he found that replica symmetry is broken. And it's broken in a particular way, and if you use this pattern of replica symmetry breaking, you can get the correct answer for the entropy at low temperature, and everything comes out beautifully. So there, you can ask a similar question. What if you hadn't used the replica? I mean, what does replica symmetry breaking even mean? This is just some trick you introduced. Like, what is the physical meaning of this? And that's something actually that the community has been discussing for 20 plus years and still hasn't really come to a consensus about, because some things that are easy to see from the replica trick point of view are very difficult to see just trying to compute directly trace rho log rho. So I think it's a fantastic question. I don't have any great answer. The calculation just does look very different if you just try to compute trace rho log rho. And I think it'd be great to understand it. There are some, you can draw funny, if you try and do trace rho log rho directly, you can draw funny sort of gravitational configurations that would contribute, but it's not clear, I think, to anyone yet how to get the same answer from that point of view. So I think it's an interesting question.
All right, thank you.
Yeah.
I also have one question.
Yeah.
So you mentioned that in theory we have to take into consideration the configurations with multiple islands and then minimize over all those configurations, right? So do you have any explicit example in your mind in which the configuration with multiple islands is the preferred one?
There's a stupid example, which is imagine you're in a context with two black holes and they're both evaporating away. Then your island region will be one in one black hole and one in the other black hole. I think that's not the crux of your question, because you're imagining like maybe a single black hole with multiple little island regions next to each other. Of course, they're generally not preferred, the fact that you have multiple islands, because having multiple islands is related in the replica wormhole point of view to having sort of higher, topologically more non-trivial surfaces. And like I said, those things are suppressed in the path integral because of the Euler character term in the model that we're considering. So that's generally why the single island configuration is preferred. From the island rule point of view, if I took this island and chopped it up into two nearby islands, I would just pick up a cost from the gravitational entropy, because I would have two additional new endpoints now, which I would have to add phi over 4g for. So the gravitational entropy would increase, and it wouldn't really lead to much of a decrease in the matter entropy. So from the island rule point of view, it's a costly thing to do. From the replica wormhole point of view, it's a costly thing to do. So in general, they tend not to be preferred. But you could construct these, simple examples of two distant black holes both evaporating away, where you would have, a two island configuration in a sense.
Gotcha. Thanks.
Sure. Okay. Well, so far I just drew some pictures and told you that they imply this island rule that was proposed by authors last year. But let's try and give like a rough argument of where this island rule comes from. Okay. So in the first paper that I cited, where we analyzed this in ADS2 coupled to flat space wings, we did a careful sort of derivation of these replica wormhole type saddles, at least for n near 1. And so we found the global solution and everything. But you can look at that paper if you're curious or ask me about it later. But the details of that are a little bit messy. I used to go over it in this talk, but I've done it a few times and I just want to talk about other stuff now. So I'll give a kind of more local argument for the island rule. And the nice thing about the local arguments is it's somewhat general. So consider some theory of dilaton gravity. Okay, so we're still in 2 dimensions. Phi still couples to the Ricci scalar in this way, but now we have some general dilaton potential. Okay, so if I picked U of phi as a constant, then I would have JT gravity in either ADS2 or DS2. And if I picked U of phi linear in phi, then I would have JT gravity in ADS2 or DS2. If I picked U of phi as a constant, I would have what's sometimes called flat space JT. But pick some, any theory you want and couple it to CFT in this way. So the CFT is minimally coupled to the metric, and it's not directly coupled to the dilaton. Okay. So that's our theory. And we're in 2 dimensions, so we can always consider light cone gauge, which always simplifies our life. And we're gonna place a defect at z equals 0 and work locally near the defect. Okay, the defect is gonna correspond in the replica trick to like the island endpoint. Okay, if we're computing entanglement entropy, we're used to thinking of inserting twist operators. Here, if we think about this as being a fixed background and computing the matter entropy, then we want to put twist operators at these endpoints. So you can place the defect at z. I just pick coordinates, so the defect's at z equals 0, and then I look at the equations of motion around the defect. This is how originally, Lufkowitz and Maldacena and other people derived things like the Ryutake-Nagi formula in the context of ADS-CFT. I'm not using ADS-CFT here. Those derivations also weren't really using ADS-CFT. They could be thought of as purely gravitational statements. So, okay, let me work locally near the defect. And I want to expand around n equals 1. Okay, I just want to recover the island rule. I don't really want to talk about replica wormholes. So for that, I need to work for n near 1. That's also similar to what Lufkowitz and Maldacena and other people have done. So I could expand the conformal factor rho, the dilaton phi, and the stress tensor of my matter, where T mu nu flat just means a stress tensor in a flat metric. Okay, if I go to this metric with e to the 2 rho, then it picks up some anomaly, but I'm basically ignoring that anomaly, same metric in the metric dz bar. So expand everything around n near 1. And the replica trick requires you to construct a smooth replica manifold, okay? In the gravitational pictures that I drew, this thing was a smooth manifold here, okay? There are these singular points here in the non-gravitational region, but this wormhole is totally smooth, okay? So smoothness on the replica manifold in terms of some coordinate W, you would write a metric dw bar, okay? That's locally near the defect, that's what it should look like to be smooth. And if you use this uniformizing coordinate, then in the z coordinates, that implies that this delta rho, the conformal piece of the metric, looks like this. Okay, this is just some general statement about defects. And there's a conformal word identity, which is basically an ordinary entanglement entropy in field theory. This is what Cardi and Calabrese used to compute the entanglement entropy from the stress tensor, from the matter stress tensor. It basically says this, that the stress tensor in a flat metric is related to the matter entanglement entropy this way, so you can get it from a residue. Bar just means also the anti-holomorphic equation. So this is how, right, I mean, these quantities don't have the matter entanglement entropy directly in them, but you get them through this relation. And the basic point is that if you look at the constraint equations of this theory, which means the GZZ and GZ bar Z bar equations of motion, if you look at those constraint equations and you expand this dilaton in a series respecting replica symmetry around Z equals 0, then the constraint equations, if you solve them order by order, you immediately get this condition, that the derivative of the black hole entropy or the gravitational entropy plus the CFT entropy should be 0. So both the holomorphic and anti-holomorphic derivatives. And this is just the extremization condition of the island rule. Okay, that island rule tells you to extremize over inclusion of regions. Here, we just considered, we sort of assumed that there was some island region. That's why there's not a complete derivation. You can look at the ADS2 paper for a complete derivation. We sort of assumed the existence of an island region and found that the replica equations of motion near the defect, which is the point at the boundary of the island region, the equations of motion there impose this condition that you extremize the gravitational plus CFT entropy. Okay, this may have been pretty quick, but the nice thing is it sort of fits on one page, and the derivation or earlier paper required a few pages and conformal welding and all these complications. Here you can get some pretty immediate intuition for the island rule, and it's more general. It works for any dilaton gravity, basically because this U of phi does not enter into the constraint equations, so it doesn't play any role. Okay, so this is some rough understanding of the island rule as coming from the replica trick. But now that we have this understanding, let me see how much time I have. Okay, well, any questions about replica wormholes and their relation to the island rule and this rough derivation? I think I want to skip to flat space and cosmology next. So if there are any questions about ADS2, please ask them now. Okay, I had a slide which I'm not really going to go over, but the basic point was, okay, you have these islands. What about all these questions about really recovering the information? Do you know what's in the interior of the black hole? And the basic point here is that you can, there's a concept of encoding the interior in the same sense of entanglement wedge reconstruction ADS-CFT. I don't really have time to go over it now, but the basic point is you can use you have the same formulas as you do in the context of entanglement wedge reconstruction in ADS-CFT. There, the statement is that by boundary degrees of freedom, you're able to reconstruct things, operators in a code subspace in the entanglement wedge. And here, the analog of the entanglement wedge is just the island region. So for a code subspace in the island region, you could reconstruct operators. There's some equality like this, which says an operator in the island region, its action on states in the code subspace is the same as an operator in the radiation region. So you can, by doing arbitrarily complicated things on the radiation, affect things in the interior of the black hole. So there's some huge non-locality in gravity, which I guess should not surprise anybody. There's huge non-locality that's not apparent by the way we usually draw pictures and write equations and things. But I'm not going to have much more to say about that. I want to talk a little bit about the extension to flat space. So this ADS2 glued to flat space, I tried to justify it by saying, well, the gravitational coupling gets strong near the ADS2 boundary, or gets weak near the ADS2 boundary. So you can do this gluing onto flat space. I think that's a good model, but it would be nice to just do directly a calculation in flat space. Okay, then you don't have to do this funny gluing. And the problem with that, or the seeming problem with that, is at first, the issue seems to be that there's gravity everywhere. Okay, if you don't have this non-dynamical region where you pick regions and compute the radiation of those regions, then you need to worry about diff invariance and all sorts of things like that. Splitting the Hilbert space and gravity and all these confusions. But in flat space, we have null infinity. Okay, and null infinity is a natural stand-in for the non-dynamical region. Okay, this is purely a choice. So when you do flat space gravity, you sort of need to decide how to treat null infinity. You need to pick boundary conditions there. And I'm going to choose boundary conditions such that gravity is basically shut off at null infinity. Okay. And if it's shut off at null infinity, then I can pick regions at null infinity and compute the entropy of regions at null infinity. Okay, it's not a time-like region, it's null, so we know how to define entropy of null regions. So that's where I want to compute the entropy. And okay, that's just talking about the spacetime. What's the model I want to consider? Well, there have been lots of dilettante gravity models with asymptotically flat boundary conditions. These were mostly studied in the 80s and the early 90s in the context of the information paradox. And the two sort of most famous ones are CGHS or RST. These are basically the same model. And they were determined at the time to destroy information. People computed the entropy of radiation. It's an exact UV complete model. They computed the entropy of radiation and found that it increases and follows the Hawking curve. So they decided, okay, these models destroy information. And that is, I believe, the correct answer for the models as they were defined at the time. So this paper that I referenced at the beginning with Tom Harmon and Andy Straminger revisited those models and considered what would happen if you sort of modified the definition of the theory, okay? If you modify the definition of the theory by saying that in the path integral, you would sum over topologically non-trivial surfaces, then we argued that then you produce answers for the entanglement entropy of radiation that are consistent with unitarity. The models as originally defined were on a fixed background. Okay, you didn't sum over different topologies. So if you do sum over different topologies, then you would have to include replica wormholes. And then you would have something like the island rule. And then if you just apply the island rule directly, which is mostly what we did in that paper, you'll find answers that are consistent with unitarity. Okay. Now, it's not clear once you sum over these different topologies how to really write down a UV complete model. So that's still, I think, an interesting, outstanding question. But the island rule does give you answers consistent with unitarity. And the pictures are something like this. So on the left, I've drawn the eternal black hole. Singular points are up here and down here. And the region R, let's say, is this region union this region. You have an island that goes across the black hole. Now, unlike the ADS2 cases, because I put the region right at null infinity, this island region does not poke outside of the horizon. It really sits right on the horizon in the limit that the region R is at null infinity. So you really cover just the interior of the black hole and nothing outside. For an evaporating black hole, the pictures are the ones that were suggested last year, where you pick a region way outside the black hole, and the island region is inside the black hole. It doesn't go all the way to the horizon. It's just a few Planck lengths within the horizon. So this is what you seem to find for an evaporating black hole. And by these entanglement wedge reconstruction ideas that I just flew by in the last slide, you get a picture of something like holographic duality in flat space. I mean, it would be nice to make this more precise, but the point is that the island region is encoded in the radiation region, but now the radiation region is at null infinity. And people often think about holography in flat space as having the data encoded at null infinity, So this is some interesting situation where something like that is true. Again, in the sense of entanglement reconstruction. The information in this region in the interior is encoded on the null boundary. Okay, so that is the situation in flat space. The argument I was giving in this slide about getting a local argument for the quantum extremal surface in general dilaton gravity applies to CGHS and RST because those models, just by field redefinition, are equivalent to flat space JT gravity. So the argument applies for them. Okay. Any questions about this? I did not have as much time to talk about cosmology as I had hoped, but maybe I'll pause for questions and then take another 10 minutes to just talk about the situation in cosmology. Okay. You can also ask me at the end. I think I sent an email around to at least some people saying that I'm happy to stick around after the talk if people have more questions. I don't have to like run off immediately. But I know, for people there, it seems to be around dinner time, but I'll be around for people who want to ask more questions later. Okay, so let's just take stock. So we've seen these island regions appear for black holes in ADS and flat space. Okay, there's obviously one other maximum symmetric spacetime. It's the one that is most relevant, I think, from these three to us, and it's de Sitter spacetime. Okay, so what about de Sitter space? Another way to phrase the question is, are cosmological event horizons like black hole event horizons? Okay, this is, to me, feels like an ancient question. I mean, obviously it's only been discussed for like 20, 30 years, but feels like it's been around since the time of Plato. And we really often focus on black holes because, well, part of the reason is because we think that it'll help us learn about cosmology and cosmological event horizons. So let's just remind ourselves what the similarities and differences are. The similarities are that cosmological event horizons have a Gibbons-Hawking entropy. Okay, if you do the Euclidean methods, you find that there's an entropy, it's A/4G, just like a black hole. Okay, and they also have a Hawking temperature. Okay, so those are similarities, that they have an entropy and a temperature. What are the differences? Well, the de Sitter horizon is more strongly observer dependent than a black hole horizon. I mean, they're both observer dependent, but the de Sitter horizon's strongly observer dependent. Another difference is that we're surrounded by a cosmological or de Sitter horizon, right? Whereas a black hole horizon can be over, you can lasso a black hole horizon. It can be over there, it's some region where the de Sitter horizon is really around us, okay? It's almost like we're inside the black hole. Another difference is that the de Sitter horizon doesn't evaporate away. Okay, we're inside of it looking out. So as it Hawking radiates, it, like, let's say a Hawking mode passes by us, it just gets reabsorbed by the de Sitter horizon again. So it's kind of like an eternal black hole. It's self-sustaining. And it's not, it's not dynamically created. This one is a little bit more subtle, but the basic point is you can create a black hole by crashing together two elephants. You can't create a de Sitter horizon by doing something like that. It's either the solution or not of your theory with some matter sources and stuff like that, okay? So those are the rough similarities and differences. And the key questions are, there's this dogma about black holes that we've believed in for a long time now, which has guided things like the Page curve and other observations, which is that a black hole can be thought of as a quantum system with A/4G degrees of freedom, and it evolves unitarily. Okay, this was given some concrete support by things like Strom-and-Dravafa and microstate counting and string theory, but we don't know that it's generally true. It's just a belief. Okay, so the question is, can a cosmological horizon be thought of in the same way? We have much less support for this. I don't know that we have any real example of microstate counting of cosmological event horizons. I mean, there's been a lot of work on it, but there's nothing I think as sharp as Strom-and-Dravafa. And a related question is the information beyond the cosmological horizon encoded within an observer's patch? So this is something that back when I was a grad student, people called cosmological complementarity. It was like an analog of black hole complementarity. which was never made precise, even there, which said that, oh, somehow the black hole is redundantly encoded on the outside. And cosmological complementarity says the same thing, that maybe the stuff behind our observer horizon is redundantly encoded in the things inside. Okay, so these island regions that I drew in a black hole are somewhat of a realization of the black hole complementarity idea. You can reconstruct operators inside the black hole region by acting on the radiation region. So we'd like to see if something like that is true for cosmological horizons. Okay, well, what's something we can do? We can do JT gravity again, now in two-dimensional de Sitter space. So before the action was phi times r plus 2. Now it's going to be phi times r minus 2. So the dilettante equation of motion will set r equal to plus 2, which fixes the Riemann tensor, which fixes it to be de Sitter space. And we're going to sort of use the same idea. Before we had these flat space wings, now we're going to have a flat space hat. Okay, some people might be used to thinking about de Sitter space as an analytic continuation of anti-de Sitter space, or as ADS sideways. This is a sort of another manifestation of that. The intuition I'm using in this picture goes a little bit beyond just flipping ADS on its side. It comes from thinking of eternal inflation and Coleman-DeLucia bubble nucleation, which says that, well, it says several things, but in particular, the hyperbolic patch of de Sitter is kind of special. Okay, so I've drawn the various regions here. In two-dimensional de Sitter space, the Penrose diagram is not just a square. Okay, the transverse sphere is an S0, which is 2 points. So you can open up the Penrose diagram into a rectangle. And you could, in fact, increase this Penrose diagram and make it as arbitrarily long as you want, and add more and more horizon regions. Okay, that's just something you can do in two-dimensional de Sitter space. And I've drawn regions 1, 2, and 3. Okay, this is identified. So this region here is identified with this region here. Region 2 is a hyperbolic patch. Okay, it has coordinates that look like this. I mean, the slices are not hyperbolic in 2 dimensions because, I mean, space in 1 dimension can't be a hyperboloid versus a line. It's just a line, but it's the analog of the hyperbolic patch. The metric looks like this, and the dilettante looks like this. Okay, time t is going from minus infinity to minus epsilon. This is like the same epsilon as you do in the gluing, or in the, you know, cutoff of ADS2 and the Schwarzian mode and all that. It's the same epsilon. And I want to glue it to region 3, which is a flat space region. So flat space in hyperbolic coordinates, again, can be written like this. And now t goes from minus epsilon to infinity. So this is a gluing of these two spacetimes. And region 1 is just another hyperbolic patch that you can think of as an analytic continuation from region 2. I mean, starting from any of these regions, you can analytically continue into the rest of de Sitter, but the particular one that takes you from region 2 to region 1 is something like this. Okay? So what you see from these is that phi is going to plus infinity over here. So using the same logic, we can say, oh, gravity is getting weak, and then we can just kind of put on this flat space hat and shut off gravity over there. We don't have to do that. We can leave gravity turned on here and use the intuition I was using in the flat space problem of saying, okay, gravity is really only shut off all the way out here at null infinity. But just for simplicity, I'll just assume it's shut off in region 3. And okay, so that's our space-time. One thing to note is this analytic continuation implies that phi goes to minus infinity at scribe plus in region 1. So you might not be able to see this is sort of on purpose, but I made this line here wiggly. It's like a singularity line, okay? So phi goes to plus infinity here, but minus infinity here. The reason this funny thing happens, well, in a second, we'll get to the reason why this funny thing happens. Okay, that's just a fact. And now we want to compute entanglement entropys again, and we can do it because de Sitter space is conformal to flat space, and we know what the single interval entanglement entropy is in flat space. So if I couple this theory of gravity to a CFT2, I know how to compute single interval entanglement entropies. And it turns out, if you go and compute, if you apply the island rule, let's say picking this region here, this blue region here, and you want to compute the entanglement entropy here, you would find an island in this region here that goes from here. Remember that these are identified with one another all the way to here, okay? So naively, this looks great. This seems to realize these things I was saying about cosmological complementarity. This is some observer back in the day, some people call this a census taker, who lives up here and just measures things in here and now has access to the stuff beyond his or her cosmological horizon. Okay, this is, this person can go all the way up to I naught, but they're still missing space-time beyond this observer horizon, there and there. Okay, so now because of the island, they seem to have access to that. Okay, this is a fake. The reason this is a fake is because of what I said about phi going to minus infinity over here. This horizon is not really a cosmological event horizon. It's more like a black hole event horizon. One way to understand that is that this JT and DS2 can be thought of as a dimensional reduction of Schwarzschild de Sitter. Schwarzschild de Sitter, if you drew the Penrose diagram of higher dimensions, looks exactly like this. And similarly, you can extend the Penrose diagram and have multiple, infinite number of regions or however many regions you want. Penrose diagram looks just like this, and this is really the black hole singularity in that Penrose diagram. So what we're seeing here is nothing more than the usual islands in the context of black holes. Now, of course, we're in de Sitter space-time glued to flat. I mean, the details are a little bit different, but conceptually, the reason this island is appearing is because this is really a black hole and shouldn't be thought of as like a cosmological event horizon. So this is a bit of a fake, but it's still interesting for various reasons. For example, if I start off here and I just think about this black hole, as I go through the wormhole, I come out here, and usually these are two separate parts of space-time. Like in ADS or flat space-time, these two parts are totally disconnected. But notice here, they're all in the past, the observable past of a single observer who lives in region 3, okay? So they're all in the observable past, so you don't need two independent, regions, which is only accessible to some sort of meta observer. This person that we sometimes call the census taker is a meta observer in region 3 and has access to all that information and therefore sees the island in the analog of the eternal black hole. Okay, I am basically out of time, but yeah, well, okay, I'm out of time. What I was going to say next is, okay, this didn't really work, so you want to think a little bit harder about pure de Sitter space, like maybe in higher dimensions, if you just do DS3, DS4, can you find islands? And there's some guiding principle for that, which is that a necessary piece of finding islands is this inequality. I won't go through the derivation, but basically you need the matter entropy to be greater than the gravitational entropy. That's a necessary condition for having an island. So then you could start thinking about regions in de Sitter space, or cosmology, which generate this inequality. Black holes do it, and FRW actually does a better job of it. If you have matter sourcing FRW instead of just pure de Sitter, you can also generate this kind of violation. Oh yeah, I guess that's all I was gonna say. But I was gonna say it more slowly. But I'll just go to the outlook and then people can ask me questions afterward. So the basic point is that these replica wormholes are a replica non-diagonal, because they couple the different replicas, but symmetry preserving contribution to the entropy and gravitational systems. That's the sort of key point, which is that we should really be doing the gravitational path integral. This mechanism is general. These wormholes, and maybe they're not saddles, maybe they're off-shell configurations. They should exist though in any number of dimensions for generic theories of gravity. There's no reason they shouldn't exist. Of course, to fully understand this, one of the things that we'd have to do is to understand the path integral of Euclidean gravity and really ensure that we should include these saddles. Okay, the first step in any saddle point analysis is just to assume that they're included. And then later you think harder and just check carefully what is the contour, or should they really be included, etc. The most important picture, one of the most important things to think about is what the microscopic picture is. By this I mean, what I've done here, what I've talked about here is the analog of Gibbons-Hawking, okay? Gibbons-Hawking computed the entropy of black holes by just doing a Euclidean trick. Okay, it was only until much later with Strominger-Vafa and works after that, including a lot of interesting recent works in ADS-CFT and higher dimensions, where we understood the explicit microstate counting. Okay, that is a real microscopic picture of what those states are. And we don't have that here. Here we just believe in the Euclidean gravity path integral, compute using it, and get answers that we expect it to be correct for other reasons. Okay, we would be wonderful to have a more real-time microscopic picture of what's going on, but we don't have that. And there are lots of other questions, but for lack of time, I will stop there and take any questions people have. Thanks.
Thank you. So, if any question, please ask from Edgar.
There's stuff going on in the chat. I don't know if that's for me or what exactly, but
Yeah, we can check.
So I have a question if I can ask it.
yeah, go ahead.
Yes, so you didn't really mention this, but I know from having seen some other talks on this that one of the features of the sort of replica trick calculations that's important is this idea that actually you should treat this like an ensemble of theories. You have this strange result that the you know, this business of you get something like a variance appearing. So you know, if you look at the overlap of two states, then you get zero. But if you look at the square of that overlap, you get something that's non-zero. And obviously, that kind of feels, you know, fits well with the idea that these JT gravity theories are dual to sort of SYK and those kind of things. But more generally, if I was thinking about, you know, obviously something like n equals 4 super Yang-Mills, which I wouldn't necessarily think of as an ensemble. And just more generally, how much of these results do you think is reliant on the kind of theories that you've been looking at and people have been looking at, and how much is actually, you know, going beyond?
That's a great question. So from our point of view, so this is actually related to what I was saying about not integrating out the dilaton exactly and things like that, because we were really viewing JT gravity as an effective theory. So the reason people started thinking about JT gravity in it as a model for black holes is that you can roughly argue that in the near horizon, near extremal black holes, JT gravity captures the effective dynamics. So if you think about it as an effective theory that way, then there's no argument that you run into these issues with factorization that you're talking about. Those issues exist, of course, if you take JT gravity as your complete theory and then you compute, as you said, and then you find these funny things that, you know, the overlap squared is not equal to the square of the overlap. So I think one of the $1 million questions is in a context where we expect there to be a single quantum mechanical theory, what exactly is going on? Do you include saddles like this one that is up here now, these Wormhole type saddles? And if you do they lead to problems with factorization? In the context that I talked about it, there isn't really an issue with factorization because, I mean, this is a bit of a cheat, but let me say it because I think it's possible that it's correct, is that here, these aren't really totally independent copies of a system that then get coupled by this replica wormhole. There are these cuts on the sheets. So these different sheets are interacting through these cuts, okay, because you've glued them together. So they're not totally independent. So there's no reason this answer should factorize in this context. Now, you can ask a related question, do related calculations, which I don't think people have done, is instead of gluing across these cuts, do something else like impose a conformal boundary condition or something like that, which really makes these sheets kind of independent. And then look to see, is there still this replica wormhole type configuration, and does it look like it dominates? Because if that's true, then it seems a little strange to say, oh, well, I should include this in the case where these sheets are glued together, but then I don't in the case where I impose this boundary condition. There are questions like that you can ask to sort of understand a little bit better when you should or should not include such configurations. And I think the name of the game is, well, different people think different things. I think that these wormholes will have a role in higher dimensional theories where they're dual to a single theory, or they just are a single theory, they're not an ensemble average. And then there's going to be some mechanism via string theory or something else that restores factorization, that doesn't imply problems that these replica wormholes naively imply. Because, you know, this is just a pure gravity picture. You have to include strings and branes and all this kind of stuff. And the question is, what is the mechanism that leads to factorization in that context? And for that, we really need to understand a UV complete theory much better than we do. So that's that's sort of my perspective. I mean, 10 years ago, if we wrote down a model and saw that the square of the amplitude is not equal to the amplitude squared, we would have just thrown it away as a crappy model. What's interesting is, okay, you could interpret it as an ensemble average, and that's sort of interesting. But yeah, I think in a string theory model, there should be some degrees of freedom which restore factorization. Or it's possible that Euclidean gravity, Euclidean gravity is not the same as Lorentzian gravity. In field theory, we have the Osterwalder-Schrader axioms. The two theories are related in a concrete way. We don't have an axiomatic framework for quantum gravity. Euclidean gravity seems to be like a trick that works. And it's possible Euclidean gravity is just computing averaged quantities in this way. I mean, there's a paper by Sully, Rosali, I think Jason Pollock and David Wakeham, I'm not sure, some group at UBC, which tries to look at how a single theory can have something like disorder averaging if it's not really dual to an ensemble. And there they basically used ideas from ETH and said, okay, by basic ideas of ETH and thermodynamics, you could think of averaging as occurring in some like little microcanonical window. So that's like another perspective on this problem.
Thank you.
Yeah.
Edgar, you also has a question in the chat box from the Matthew. He asked about
Yeah, so the question is, could the replica symmetry breaking affect any magnetic properties in the case of a magnetically charged black hole? I don't know the answer to this, basically because I don't know, well, first, I don't know if replica symmetry breaking is actually an important effect in this context. There are these saddles which are replica symmetry breaking, which I talked about, where like, let's say you connect 2 of these sheets and then leave the other 4 disconnected. That's a replica symmetry breaking saddle, but those things never dominate. So there's no context that I'm aware of so far where such things dominate an ensemble. But one obvious thing is, as you increase the number of sheets, there becomes entropically a large number of ways to connect these things that break replica symmetry. Still, no single one of them dominates. So I think part of an interesting question is to find a situation where replica symmetry breaking becomes important. I think it's going to be related to doing calculations. Often when I was doing these calculations, I was working a large central charge. I wasn't assuming that the theory was holographic. I was just doing large central charge because I didn't want to worry about the graviton, because we don't really understand very well how to compute entanglement entropy of gravitons. And once the graviton comes into the game, it could play more of a role in leading to replica symmetry breaking saddles. And it might be connected to an old story of Ananos and Denef, where they observed replica symmetry breaking in cosmology, actually. It would be interesting if replica symmetry breaking saddles played a role in their context and their concrete calculations you can do there, which nobody has done. But it could be that they play a role there. I don't know in the case of magnetic charged black holes, because I don't know of a reason that such saddles should dominate. Yeah.
So any other question?
May I ask a basic question regarding information paradox, information loss paradox? So this is not kind of off topic, not related to your interesting calculation and
Totally fine.
But just go back to the premises and assumption about the information loss paradox. So usually in quantum mechanics, when we go to macroscopic level, we lose interesting quantum effects like superpositions or entanglement and things like that. For example, like in a double slit experiment, as long as the electron is flying, it's a wave function, but once it hits the screen, the wave function collapses. Now, in the information loss paradox, we have a radiation that's coming out, and the radiation, the part of that goes inside the black hole. So why the collapse of the wave function is kind of neglected in this problem. And people don't say that like a black hole as a macroscopic object is observing the radiation and cause the radiation to collapse.
So I'm not sure I understand the part about the radiation collapsing. What, can you repeat?
So I'm saying that, so at that level, we usually, it's hard to know whether the entanglement exists or not. So we usually don't see entanglement existing between macroscopic objects or superposition of wave function at macroscopic level. But in quantum gravity, we are treating black hole as a quantum object and kind of neglect collapse. So we are saying that the evolution and everything is unitary. So collapse is nowhere in this picture.
Yeah.
I'm asking, yeah, how is that possible?
Well, as long as we don't get into discussions of how you apply things like decoherence when there's a closed universe, if we don't get into those discussions, then I think it's fine to treat the entire system. I mean, everything should always be treated quantum mechanically. And the fact that things appear classical are, I think, like what you're saying is when something is bathed in a large number of degrees of freedom, and the large number of degrees of freedom effectively collapses the small number of degrees of freedom. But in this context, I think the calculations are effectively done reliably in that you can treat the system quantum mechanically. You will see that the correct treatment is always a pure quantum mechanical one. There isn't an additional rule we should put about X collapsing Y or something like that, unless we're trying to do some approximation and measure something in a lab or something like that. And in that context, I think there's, radiation that appears, it has a, fine-grained entropy, which you can compute, and there's no additional rule that you should input about something or other collapsing a wave function. You're just treating the thing quantum mechanically, computing a reduced density matrix, which is always okay if you treat the full system quantum mechanically, and then computing the entropy of that reduced density matrix. It's possible that I'm missing the point of your question, but that is my perspective on the problem, that it's just treated purely quantum mechanically, and that's always okay. You don't ever have to talk about collapse of wave functions when you do that.
Well, if we do the same procedure for the double slit experiment, we never get a collapse. But we do observe collapse there. So that's kind of apart from the unitary evolution of the Schrödinger equation.
Yeah, but the question here is just phrased as the entropy of the radiation. I mean, I think you might be asking a more sophisticated question of inserting an observer into the mix. For example, in the double slit experiment, if you just evolve the equations of the apparatus and whatever's going through the apparatus quantum mechanically, indeed, it wouldn't collapse. You just get some full wave function for the system. It just evolves however it evolves. So maybe to answer your question, yeah, the analog of what we're doing, as you said, is there's no need to collapse things at the end. We just take the full system, apparatus plus whatever's going through it. We evolve it unitarily to produce some final wave function. And then we just chop up that wave function. We compute pieces, the entropy of some subregions and things like that. So that's the analog of what we're doing, because that's the place where the paradox is sharp. It's like if you evolve the double slit apparatus and whatever's going through it, and then found that some single state psi evolved into bra I, ket I, summed over I, pure state into mixed state. If you found that, then you'd back up and say, okay, I don't want to collapse anything. Let me just see why this is happening. And so the name of the game in the black hole setup is to, in that context, where you just take the global system and it evolves quantum mechanically, you don't, as an external observer, come and collapse anything. You just want to be able to compute the density matrix in the final state. I didn't compute the density matrix, or no one has. We just computed the von Neumann entropy. But even at that basic level, there is an issue with the information paradox of just some closed system evolving in time.
Mm-hmm. Well, I see. Well, going back to the double slit experiment, one can say that the observer is not the person who watches the experiment, but is the screen. And with analogy, the screen here is the black hole that is observing the electron and positron and things that come out of a vacuum. So if the black hole as a macroscopic object is an observer, then that causes the collapse of the wave function. And then we don't get to the point of the paradox at all. There is no entanglement entropy.
Well, I think in this context, the black hole is treated quantum mechanically. And again, the equations are evolved quantum mechanically. So again, it's just a closed system that evolves in time. And I think it's an important question there to compute the entropy of the radiation and show that it is consistent with the closed system evolving in time. I don't think that there's any out which allows you to say, for example, in the calculation I was talking about, it wasn't really even a black hole. It was just Rindler space. So in the 2D context, you have a problem even with Rindler space, which is just the vacuum. So there, there's no higher dimensional Rindler space problem, but in 2D, it's sort of special. And there, we know what the correct quantum mechanical evolution is in the context of a fixed gravitational background. And the name of the game was how to understand the correct quantum mechanical evolution when you also introduce gravity. I mean, the stuff you're saying, I think, is a little bit more related to having a more physical picture of what's going on. For example, people often, I flew by this, but in the entanglement wedge reconstruction ideas, you often talk about doing various operations on the radiation. And there are things you can do to the radiation that will, collapse the wave function, and in particular do certain things like introduce a firewall at the horizon and do funny things in the interior of the black hole. So I think what you're asking about is more relevant in that conversation when you put an observer or a quantum computer that does manipulations to the radiation and then affects thereby the interior of the black hole. But if you don't put in such observers or whatever, then you just have some closed system evolving, like, a gas in a box. You can say that a big part of the gas collapses the wave function of a small part of the gas, but you don't ever have to say it. You can just evolve the full system quantum mechanically and then ask questions about reduced density matrices. So that I'm viewing it in that context, which I think is the more fundamental description.
I see. Thank you.
Yeah.
Edgar, I will stop the recording of the video, but we are stay to people ask any question whenever you are okay.
Sounds good. Yeah. I'm happy to stick around for a little while.